Last week we were talking about electric fields, and in particular we were talking about the electric fields produced by point charges. Today we want to talk about slightly more interesting charge distributions and how we might go about calculating the electric fields that they may produce. As an example, I want to show you what a parallel plate capacitor is. Okay, a parallel plate capacitor is essentially two pieces of metal, two plates of metal. Okay, so this is a metal plate. It's oriented kind of perpendicular to the board. We're looking at sort of a cross-section of this thing. And another one. So in fact there are two metal plates, separated by some distance. What I want to imagine doing is taking from the top plate a bunch of electrons and plopping them on the bottom plate. Okay, I can do that with, for example, a battery. That means that the bottom plate is going to acquire a net negative charge, and the top plate is going to acquire a total positive charge that's equal in magnitude. Okay, and the question is, what type of electric field is such a charge distribution going to create? Now we clearly can't think of a plate as a point charge, right? That's obviously unphysical. That's not how we can think about this. We could imagine coming at answering this question a number of ways. We could say, well, okay, let's imagine, all of the millions and billions of little infinitesimal point charges that comprise each of the metal plates, take the vector sum of the electric fields created by every single one of those guys, add them all up, and I would know the electric field at whatever point in space I choose. And in fact, that is a reasonable approach. Sadly, we would need calculus to do it, and that's sort of outside of the tool set of this class. But it turns out that there's actually a much easier way to do it, and that's the way I want to talk about it today. I'll just go ahead and start by telling you the answer. The answer is when I have two of these metal plates like this, I get an electric field that points from the positive plate to the negative plate. That should be no surprise. And in between the plates, far from the edges of the plates, the electric field is uniform, very close to uniform. Now it turns out that towards the edges we start to get this characteristic bending of the field lines, kind of like this. In fact, we call these the fringe fields. But my real question here is how, given the total charge on each one of these plates, how can we calculate what the strength of the electric field between the plates would be? And again, with the tools at our disposal currently, we can't do it. We need to talk about a new concept called electric flux. Now, I want to start with something that may sound weird. I'm going to draw on the board an imaginary surface. In this case, something like a sheet of paper. So you can even think of this as an imaginary sheet of paper. And let's just say, for the sake of argument, that it has a certain area A. Now, the way I'm trying to draw this, I want you to try to picture this thing as being kind of perpendicular to the board. So, in 3D, it would be kind of like this paper right here, right? So this is kind of what I'm imagining right here, is that it's actually oriented perpendicular to the board, like this. And let's say that I put this imaginary sheet in a region where I have set up an electric field. So let's say I've got some positive charges over here, some negative charges over here, so that the net result is that my electric field is roughly uniform, let's just say, and it points to the right. Now you can see that as the field lines come in from the left, they're going to poke through my sheet, right? So I'll try to draw that, poking through there. Maybe this one pokes through there. This one might poke through right there, right? But here's my electric field lines. Again, the imaginary sheet has nothing to do with this electric field. It didn't set it up. I set this electric field up with some other charges that are out, outside of the region of this picture. All I'm doing is I'm putting this sheet of paper in the presence of that electric field. Now, electric flux is a measure of how much electric field pokes through that surface. So in this context, the electric flux, by the way, the symbol I use for electric flux is going to be the capital Greek letter phi. And in this context, the flux is going to be directly proportional to the field, the strength of the field, which makes sense, right? Because if the electric field were stronger, the field lines would be more compact. And also, if I had a bigger sheet of paper, I would have more field lines poking through too. And so it's got to be proportional to the area. But it turns out that this is not the most general definition of electric flux, because I can do some other funky things, right? I can take my sheet, for example, and rotate it like so. I could rotate it like this in this electric field, and both of those things would affect the number of field lines that are poking through the surface, right? So to illustrate this, I'm going to extend these field lines a little bit farther, so I'm going to have them go all the way up across the plane of the page. So my electric field is uniform and points to the right, all in the board here. And let's imagine now rotating this sheet of paper such that it's now parallel to those field lines. It's going to look something like this. I've essentially laid this thing on its back. In this case, I hope you can see that none of these field lines are actually going to poke through the surface now. So in this case, the flux is 0, right? So absolutely it depends on how the sheet itself is oriented with respect to the electric field. And in fact, more generally, if I have an angle that's somewhere in between these two extremes, if I have something more like this, right, then I'm going to have some field lines poking through, but not as many as I did over here. So how much electric field is poking through this surface? Well, to answer that, what I do is I define an angle, which I'm going to call theta. And that angle theta is going to be measured between something that I'm going to call the normal line. Now, a normal line in this context is just going to be an imaginary line that's perpendicular to my imaginary surface. So like this pen, perpendicular to the surface, right? And the angle between the direction of the electric field and the normal line is going to be my angle theta. And so the most general way to write the electric flux through this imaginary surface is to say that it's EA times the cosine of this angle phi. Why? Well, it's cosine because in this case, when the sheet is vertical, the normal line is like so, which means that the angle between the normal line and the electric field is 0. And cosine of 0 is 1. And so I have EA times 1. Over here, the normal line is perpendicular to the electric field, so cosine of 90 is 0. So I got a 0 there. So you can see that this really does cover the full possible range of all these possible values. Okay, so we have a general definition now for electric flux. Now I need to make an important distinction between the types of surfaces I was just drawing, which I call open surfaces, and closed surfaces. Right? The fundamental difference is that an open surface, like a sheet of paper, like we were just drawing, contains no volume. Right? It doesn't bound anything. A closed surface would be like a bag, like a garbage bag, a closed garbage bag. It contains volume. Right? And so it's an interesting question to think about electric flux in the context of a closed volume. So like a closed surface, which I'll call S. And I'll draw it in kind of a funny shape so that you can see that it's kind of general what I'm talking about here. So here's my closed surface, which I'm calling S. You'll notice that every time I'm drawing one of these imaginary surfaces, I'm using red ink. And I'm kind of doing that on purpose because I want you to always understand that when I'm drawing something with this particular color, I'm talking about an imaginary surface. This is not a real physical bag. It's not. It's just something that we're imagining. Take this surface, this closed surface, and let's put it in the uniform electric field. I'll draw this one pointing sort of up and to the right. Now the electric field coming in, it's going to poke into the bag, say, it's going to spend a little while wandering through the bag, and then it's going to poke out again, right? This guy might come in, poke in here, stay inside for a little while, and poke out on this side. Another electric field line may come in, poke in, right? So here are my electric field lines, right? At this point, I need to adopt some conventions when I'm talking about electric flux. Number one, if the electric field line pokes into the imaginary surface, S, then the contribution to the total electric flux is going to be negative. So over here, for example, when this field line pokes in, right, this would correspond to a negative contribution to the total electric flux through the surface. If the electric field pokes out of the bag, then the contribution will be positive. So if as in this case, the two are balanced, if balanced, then the total electric flux is 0. So this is the type of situation we're in here. You'll notice that every electric field line that pokes into the bag also manages to find its way out of the bag, right? All three of them in this case do. And so we can say that the electric flux through this surface is 0. Even though the area of this surface is not 0, nor is the electric field 0. So looking at this picture sort of begs the question, under what conditions could I possibly have a non-zero electric flux through a closed surface, right? Clearly it won't do the job if I have some positive charges over here, some negative charges over here, and an electric field poking through the whole thing. That clearly doesn't give me any electric flux through this surface. What I have to have in order for there to be an electric flux through a closed surface, there must be, and I hope you can kind of visualize this, there must be a charge somewhere inside of the surface, right? Because if there were a charge somewhere inside, then I would have field lines poking out of the bag, right? And no field lines poking in if it were a positive charge, right? Let's start with a simple example. Let's imagine that I've got a positive point charge. Let's start there. Very simple. Positive point charge, magnitude Q. And let's say that surrounding that point charge at some distance r, I've got a sphere. So it's centered on that charge. And I'm interested in what the electric flux through that sphere would be. So here's my positive charge. You guys know that this positive charge is going to set up an electric field. That's going to look something like this. It's going to point radially away. And all those field lines are going to go out to infinity. Okay, so what I'm doing here is I'm imagining one of these Gaussian surfaces, I call them, right? This imaginary open surface, and it's centered. It's centered on my positive charge. Has some radius r. So this is my imaginary surface. That's why I'm drawing it red, right? And you have to kind of picture it as being a three-dimensional thing, right? And so the question is, what is the electric flux through this surface? The flux, which as you recall, is E times A times the cosine of this angle, theta. So let's pick this apart one by one. Well, we know at some distance r away from a point charge, we know that the magnitude of E is going to be K times Q over r squared, right? So at all points on this surface S, that's the magnitude of the electric field. Okay, so we've got the E portion. What about the A? Well, in this case, we're talking about the surface area of a sphere. You guys may not remember this, but that's just 4 pi r squared. Now what about this cosine theta? Remember that the angle theta is measured between a line perpendicular to the surface and the electric field at that point. So, for example, let's look at a point right here. There's a field line poking out, right? In what direction is the normal line? Well, in this case, the normal line, which is a line perpendicular to the surface, would point in the same direction as E, right? Similarly, over here, the normal line would point also in the same direction as E, right? So the benefit of having an electric field that always points perpendicular to the surface is that the angle theta is always 0, right? The flux would then be E, which is kq over r squared, times A, which is 4 pi r squared, times the cosine of 0, which is just 1. And so I've got it. It is 4 pi k, the r squareds cancel, q. That is the flux through my surface. Right? So that's the answer to the question. Now I'm not actually going to stop there because I want to mention to you something that is going to be a little bit annoying, but it's just purely historical. So for historical reasons that, again, are going to be slightly a bit of a nuisance for you. We define a new quantity called epsilon 0, which is called the permittivity of free space, and we define it to be 1 over 4 pi k, right? There's nothing deep about that whatsoever. I can define whatever constant I want, right? We're going to use this quantity lots and lots of times over the course of the semester, so it's best for us to get comfortable with it now. That means that k is equal to 1 over 4 pi epsilon 0. By the way, again, these are all just constants. 4 pi k, 9 times 10 to the 9, right? So if you plug all that in, you find that this is about 8.85 times 10 to the minus 12, right? And I'll give you a second to work out the units. Pause the video and work out the units. Okay, hopefully you did that. Units in this case are coulombs squared per Newton meter squared, right? So this is a useful constant to bear in mind. It's the permittivity of free space. Now, I want to use that definition in this formula right here. So plugging this into here gives me, for this question, a flux equal to, so if you plug this in for k, the 4 pi's cancel, you just wind up with an epsilon 0 on the bottom, q over epsilon 0. So this is the answer to our question, right? What is the flux through a sphere of radius r centered on a point charge q? What if it had been a negative point charge? Well, this would have been a negative q, which means that the flux would have been negative, but that makes sense because then all the field lines would have been poking into the bag, right? This is a very fundamental result because it turns out that for any closed surface, S, that you can think of, the flux through that closed surface is going to be equal to the charge enclosed by that surface divided by epsilon 0. This is a general truth. It's true in the simple example that I showed you, but it's true, in fact, for all possible closed surfaces and all possible arrangements of charges inside that surface, right? This is the famous Gauss's law that I've been advertising, okay? It doesn't look like much, but in fact, it's a very fundamental and very important and useful tool. I'm not going to prove this to you generally. It worked in the simple case that I showed you, and it works in all possible cases. And in fact, I do actually have quite a nice graphical proof of that, which I can show you if you're interested. You can come to my office hours. I can at least convince you in a certain situation that it should be true. So for example, let's revisit our old friend, the electric dipole, which we talked about a couple of times. Right? An electric dipole is simply a positive charge and a negative charge separated by some distance. The electric field lines set up by such a charge distribution look like this. right? And I want to imagine enclosing both of these charges by some imaginary shape, right? So this is a bag, and it encloses both of these charges. So this is my imaginary surface S. Again, it's nothing real. There's nothing there. I'm just imagining it, right? And I can ask the question, what's the electric flux through that surface? Well, in this case, the total charge enclosed by the surface is plus Q minus Q, which is 0. So according to Gauss's law, that means the electric flux through that closed surface must be 0, right? And that makes sense because look at all of these places where the electric field either pokes in or pokes out of the bag. Here it pokes out of the bag, here it pokes out of the bag, out of the bag, out of the bag, out of the bag, at all those spots. But over at these spots, it pokes in, right? Every field line that pokes out of the bag also winds up poking in. So I have just as many positive contributions as I do negative contributions, right? Just as many field lines are leaving the bag as are entering, right? And it's because the net charge that I'm enclosing is 0. So there is a very important relationship between the charge enclosed by an imaginary closed surface and the electric flux through it. Now, so that's all fine and good. But what is electric flux good for? Well, two things in particular, and we're going to see plenty of examples this week on how to do this. But it's really good for two things. Number one, it is good for calculating the electric fields created by charge distributions that have a high degree of symmetry, right? Such as, for example, the parallel plate capacitor that we started with today, right? We're going to talk about that in class in the coming days. Number two, if you're given the electric field, right, if you know the electric field in some region of space, then in fact you can use that to figure out where the various enclosed charges might be. We're going to see some interesting applications with that in mind, especially regarding conductors. So that's coming this week.